Hi, organic chemistry students. Today's screencast is on chair and boat conformations of cyclohexane. So the chair conformation is the most stable conformation of cyclohexane. And I've got a model of cyclohexane that we're going to use here to talk a lot about cyclohexane. So if I start off with my model and I actually make it planar, let's pretend for a second that cyclohexane really preferred the planar conformation. And if we did that and we looked at its hydrogens, what we'd find for those hydrogens, and really make sure that it's all planar, is we'd find that these hydrogens are really all eclipsing. Now, I have to point out that on my cyclohexane, I placed white and the green atoms as hydrogen atoms. The reason I did that, green is usually a halogen, like a fluorine, chlorine, bromine, iodine. I'm going to use a green to represent hydrogen to show you something in just a minute. So for now, let's say that all of the green and white are hydrogen. And then let's go ahead and if we stare down a carbon-carbon bond, what we notice is a lot of eclipsing of these hydrogen atoms if it were all planar. So if cyclohexane were planar, you'd have a lot of eclipsing. Okay, so a lot of torsional strain. And then you'd have more ring strain because actually you're not at the ideal bond angle just yet. You haven't reached that 109.5 degree bond angle. And so to reach that perfect tetrahedral bond angle, what the carbons do is one end of the molecule actually pops itself up to be what's called the head of the chair. And the other end of the molecule actually kind of pops down here to become what's called the foot of the chair. And then we need it to be angled just slightly. And so we've got head of the chair and we've got foot of the chair. And then we can twist it the other way if we want to look at the opposite chair conformation. And if we make the opposite chair conformation, looks a little bit like this. And now my model matches the model that you can see on the screen because I've got the head of the chair right here, and then I've got the foot of the chair right here. Okay, so if we look at this on our screen, what we have is we actually have this spot right here will be what's considered the head of the chair, and this spot right here will be what's considered the foot of the chair. This portion, if you will, is like the seat. So here's like the seat of a reclining chair, like a lazy boy. And again, head of the chair, foot of the chair. So that's the idea. Now, in the chair conformation, we have 6 hydrogens that are axial, so their bonds are straight up and down. And so when we're looking at axial hydrogens, the 6 that are axial are here. 1, 2, 3. 3 that are axial down, and 4, 5, 6. 3 more that are axial straight up and down. We have 6 that are equatorial. And so those 6 that are equatorial are coming out at angles. So 1, 2, 3, 4, 5, 6. And those angles are just slightly above or slightly below a horizontal line. And so we've got the head of our chair right here and the foot of our chair right here. And we've got these 1, 2, 3 axials that are straight up and down, and 1, 2, 3 straight up and down. So 3 axial up and 3 axial down. And so that's where I've used all my green atoms. And then if we look right here, all of my equatorial atoms right now are white. So I've used the white to show my equatorials, and the green are showing my axials. Now you can see why I wanted to use green and white for hydrogen, even though green are normally supposed to represent halogens. So then I can do that chair flip that I've kind of shown you a little bit and alluded to a little bit already. Now, if I've got the chair that's on the left right now, and I want to flip it, all I do is take the head of my prior chair and bring it down to become the foot of the chair. And then I bring the old foot of the chair up to become the head of the chair. And I have to do a little bit of twisting to make sure that everything is lined up straight up and down. So now this has become the foot of my chair, and this has become the head of my chair. Now, I want you to watch the colors of the axial and equatorial hydrogens this time. Notice how in this chair conformation, all the axial hydrogens are white. Gosh, that doesn't seem right. Weren't they all green? We'll watch the flip again. So head will come down, be foot, foot will come up, become head. Look at that. The axials became green. Okay, so upon chair flipping, the axials go from green to axial white. And chair flip again, white goes to green axial. And so these axial hydrogens are the ones that are straight up and down, and now white is coming out equatorial. And when I flip it, I'll show you one more time. I've got axial white, and equatorials are all green coming out. And so whenever we do that chair flip, what we're doing is flipping any hydrogen or group that was previously axial, and we're making it equatorial, and vice versa. So they just swap their positions, axial for equatorial, upon a chair flip. So let's study our line angle drawings just a little bit. I'm going to do a separate tutorial next on just line angle drawings. So you want to focus on that to learn how to draw the bond angles correctly. Now, in the middle of that chair flip, there was something interesting going on. If this is one of my chair conformations, and I go to take the foot of my chair here, I'm going to take the foot here, and I want to make it the head of the chair on a chair flip. There's this moment where both heads of the prior chair and the new chair are up, and this conformation is called the boat, where it looks like this is the base of a boat, and this is like the bow and stern of a boat. I'll try to take my hands away so you can see that kind of bow and stern of that boat conformation. So this conformation is not favored because of this eclipsing, this lining up of hydrogens left to right, here and here, here and here. There's a lot of eclipsing of hydrogens that's going to lead to torsional strain. Plus, there's a lot of steric strain here because the electron clouds of these two hydrogens are sometimes referred to as these flagpole hydrogens. They're bringing their electron clouds quite close together and have a lot of steric strain because they've come too close together. So it's not a favorable conformation whatsoever. So if we look at the chain of events of what happens to cyclohexane, we can start off with one of our chair conformations on the left, where we have the head of the chair up, on the far left, and the foot of the chair down. We can take that foot of the chair, bring it up to momentarily make this boat, which is not favored. Not favored because of this steric strain, not favored because of all of this torsional, eclipsing strain. So this boat is not a favored conformation whatsoever. And then we're going to bring that down and make the opposite chair conformation. That's just the cycle of how it goes chair to boat to chair. So what if we were to put some groups on cyclohexane? Let's go ahead and remove a hydrogen here to place a group onto cyclohexane. So what if we go ahead and remove one of our hydrogens and place a methyl group onto cyclohexane? So what we want to do is create the molecule on the left And on the left, we have the head of the chair up on the far left, the foot of the chair down on the structure on the left, and then this methyl group coming out equatorial. And let's just go ahead and flip it. Let's bring the foot of the chair up, bring the head of the chair down, and sure enough, it flips to axial. And so now this methyl group is in the axial position. What we see in the axial position are that these groups are much closer together. There is a lot more steric strain right here. And so if we flip it again to go back to that equatorial, just to kind of compare for a visual, when we look at our model, it does appear that the methyl has got more room when it's out equatorial. It's not as close to these neighboring hydrogens when it is out equatorial. When I kind of take a look at it, it just seems like that methyl group has quite a bit more room equatorial than when I flip it to axial and I look at some of the neighboring hydrogens. I've got to get all my axials straight up and down. We're looking at closer to the neighboring hydrogens, and that's going to cause more strain and be less favorable. So when we look at this kind of strain, steric strain between that big methyl group and the neighboring hydrogens is much worse when the group is axial. So they prefer being equatorial. Now, cis and trans isomers can, in theory, and are sometimes drawn planar. So that for trans, if we look at trans 1,4, we've got one methyl that's represented up and one methyl that's down. So that can also be represented as a wedge and a dash. Or for cis, we've got two methyls that look like they're down, cis on the 1 and the 4. So here they're both drawn with dashes. They could be both drawn with wedges. For the cis 1,4, it's possible to draw them planar. It's just not so useful. It doesn't depict how cyclohexane really wants to be, and that's in that chair conformation. At this point, you might start wondering, I'm not sure if this is an organic chemistry lecture or if it's just hexagon drawing class. Valid question at this point. Sometimes it feels like we have drawn a lot of pentagons and hexagons. So cis-trans isomers are most often represented as chairs because that's going to give us a lot more information about the molecule and be much more useful than drawing those flat hexagons. So you don't have to worry about hexagon drawing class, but you do have to worry a lot about chair drawing class. So make sure to watch the next screencast on drawing chairs properly. So groups that are equatorial in one chair often want to be axial, flip to axial in the other chair. So let's study trans 1,4 dimethyl cyclohexane. If I want to be sure that I'm making trans 1,4, I can go ahead and pretend that the molecule wanted to be all planar and go ahead and try to make it all flat and planar. And I have one methyl here, and I want to go to the 1, 2, 3, 4, which is directly opposite. If it's going to be trans, I have one methyl coming out at you. That means I need one methyl coming back at me. Now, let's see what happens when we go to put that into a chair conformation. Okay, this is looking like the structure you are seeing on the left, where we have this methyl group that is up axial and a methyl group that is down axial. Remember, we said when these groups are axial, they don't have much room here. There's a lot of strain here, these electron clouds coming together. So let's try to flip it. So if we go ahead and we bring the head of the chair down to become the foot of the chair, up to become the head of the chair. And usually we have to do some adjusting before it's going to look like a chair again. And we go ahead and we look at these axial hydrogens. What we see is now the groups are coming out. Here is our methyl out and on the far right. And here is our methyl on the out equatorial and on the left part of the drawing. And so now we've got our two methyls that are out equatorial, and they've got a lot more room, and so this is going to be really highly favored. And the way that we show this is with a larger of the two arrows going to the right. That really shows that that's favored, and that the line for the arrow to the left should be smaller, showing that we're going to favor that what we call a di-equatorial version of the trans 1,4-dimethyl cyclohexane. So let's change to cis 1,4. One way of doing that again is to pretend that your whole molecule wanted to be planar. And then to make it cis, we actually have to pull the methyl group off of the molecule and put it in a new spot. So that tells you a thing or two about cis-trans isomers on cyclohexane, that you have to remove that methyl group in order to place it back onto the chain. So now I have them both coming out at U, cis, when it's flat, but we know it doesn't want to be flat. It's going to instead now I want to try to show you the same thing that you are seeing. So on the far left-hand side, we've got a chair that looks like this, where its methyl group is down here at the foot of the chair. And then we go from the 1, 2, 3, 4. At the 4 carbon, there's a methyl group that's equatorial coming out and down on the right-hand side of the chair. And so now we want to flip that. So what we notice is that we have one methyl group that's axial and one methyl group that's equatorial. And we want to go ahead and we want to flip that. And so we'll take the foot of the chair, bring it up, take the head of the chair and bring it down. And what we'll notice, oh, and unfortunately I got one of my methyls switched. When I switched them out, I didn't switch the color. There we go. All our axials are green now. What we notice is when we flip that, well, again, we have a methyl that is equatorial and a methyl that is axial. The one that was axial before just switched to equatorial now. The one that was equatorial before switched to axial now. And so we've got one of each. In both conformations, there's an axial and an equatorial, and that really means that they're going to be equally favored. So what we notice is that those two conformations, since they're of equal stability, one in the equatorial, one in the axial position, are going to be equally favored, and we would draw those arrows the same size in both directions, or draw equal arrows in both directions to show that the two conformations are of equivalent stability. So that should give you a little idea of how the chair and boat conformations of cyclohexane are used in drawings and representations.